In June 1956, workers at an IBM facility prepared to move a machine unlike anything most people had ever seen. It was not a computer in the modern sense of a small box sitting on a desk. It was a towering storage cabinet surrounded by control equipment, cables, motors, and a separate air compressor. Inside the cabinet stood a vertical stack of 50 aluminum disks, each one 24 inches across. They were wider than many modern computer monitors, and heavy enough that the complete storage unit weighed more than a ton. When the system started, the disks accelerated together until they were turning at 1,200 revolutions per minute. A mechanical arm moved between them, searching for information on magnetic surfaces, while forced air kept the delicate read and write heads from touching the spinning metal. All of this machinery existed to store 5 million characters, an amount of information that today could fit into a tiny fraction of a memory card. A single modern photograph can occupy as much or more storage than this entire machine could hold. Yet, to compare the IBM 350 only by capacity is to misunderstand what it accomplished. Its purpose was not to impress the future with a large number. Its purpose was to solve one of the most frustrating problems in early computing: how to find one specific piece of information without searching through everything that came before it. The machine was part of the IBM 305 RAMAC system, whose name stood for Random Access Method of Accounting and Control. It became the first commercially shipped hard disk drive. And although its 50 giant platters now look almost absurd, the idea inside that cabinet changed the relationship between computers and information forever. The story of why IBM needed 50 enormous disks begins before hard drives existed, when data lived in paper cards, magnetic tape, and rooms filled with cabinets. In the early 1950s, large organizations were already drowning in information. Businesses were beginning to use electronic computers for calculations, but the machines still relied heavily on methods inherited from mechanical tabulating systems. The most familiar storage medium was the punched card, a rectangle of stiff paper with holes arranged in rows and columns. Each pattern represented numbers, letters, or instructions. One card might describe a customer, a payment, a product, or a single transaction. A large company could generate millions of cards. Those cards needed cabinets, trays, labels, sorting equipment, card readers, and trained operators. They also needed discipline. A card placed in the wrong stack could effectively disappear. A box dropped on the floor could scatter records into chaos. Cards could bend, tear, absorb moisture, or burn. Even when everything remained perfectly organized, obtaining an answer often required moving physical stacks through several machines. Magnetic tape offered much greater capacity and could feed data into computers automatically, but it usually worked in sequence. If the desired record was near the end of a reel, the system had to pass through the material that came before it. Tape was like a long road with no direct exits. It was excellent for reading large files from beginning to end, but poorly suited to a business question that demanded one account immediately. Imagine a clerk asking for the balance of a particular customer. With cards, someone might locate the correct group, sort the deck, and run it through a reader. With tape, the machine might search along a long sequence of records. The result could take minutes, hours, or even longer when a complete business process was involved. Computers could calculate rapidly, yet they often waited for information to arrive. Engineers began to understand that faster arithmetic alone would not transform business. A computer also needed a way to reach stored information directly. One of the people asked to solve this problem was Reynold B. Johnson, known to colleagues as Ray. Johnson did not begin his career as the obvious father of a new computer industry. He had been a high school science teacher in Michigan, where he designed a machine that could detect pencil marks on standardized test sheets. The invention combined mechanical movement, electrical sensing, and practical data processing. IBM initially showed little interest, but the idea eventually brought Johnson into the company, where he spent years creating devices related to punched cards and automatic information handling. He developed a reputation as a restless inventor who preferred physical experiments to abstract arguments. In 1952, IBM sent him west to lead a new laboratory in San Jose, California. At that time, the area had not yet become famous as Silicon Valley. The assignment was broad: investigate new methods of storing and retrieving information. Johnson gathered a team of engineers with different specialties. Among them were Louis Stevens, William Goddard, John Honstra, Arthur Critchlow, R. Manning Hermes, and many others whose combined work would turn a risky concept into a commercial product. The invention was never the work of one man drawing a complete machine in isolation. Johnson's importance lay partly in creating the environment in which the team could explore competing ideas. They considered wires, strips, drums, tapes, cards, rods, and rotating magnetic surfaces. Johnson later remembered 2 decisions with particular pride. The first was to concentrate on random access, meaning that the system should reach a chosen record without moving through every earlier record. The second was to concentrate on laminated or stacked disks. Neither decision guaranteed success. At the beginning, a stack of large spinning plates looked more like industrial equipment than memory. Some observers compared early models to a meat slicer, but Johnson's group was not trying to make something visually elegant. They were trying to turn stored information into a resource a computer could request on demand. Magnetic drums already demonstrated that data could be recorded on a rotating surface. A drum was a metal cylinder coated with magnetic material, with reading heads positioned along its length. As the cylinder turned, each head could detect or change magnetic patterns passing beneath it. Drums were faster than paper and could provide direct access to tracks, but increasing their capacity created difficulties. A larger drum became heavy, expensive, and mechanically demanding. A longer drum required more space and precision. The IBM team saw an advantage in flat disks. Each disk offered broad circular surfaces. A stack of disks could place a large recording area inside a cabinet without requiring one enormous cylinder. A movable arm could select a disk level, travel inward or outward to a track, wait for the correct section to rotate beneath the head, and then read or write the requested record. The concept sounds obvious today because generations of hard drives use the same broad arrangement, but in the early 1950s it raised a frightening list of questions. Could large disks spin rapidly without vibrating? Could a magnetic coating be applied evenly enough for reliable signals? Could a head move quickly between surfaces and return to the correct track? Could the head approach the disk closely without scratching it? Could the machine survive daily use in a customer's office rather than a protected laboratory? Could electronic circuits interpret weak signals from tiny magnetic regions while motors, relays, and other equipment generated electrical noise? The team built experimental rigs, tested coatings, measured vibration, studied airflow, and repeatedly changed mechanical designs. The disk idea was attractive because it promised random access, but that promise depended on solving several problems at once. A disk that stored data but damaged itself was useless. A head that moved quickly but missed the track was useless. A surface that worked in a laboratory but failed after months of rotation was useless. Commercial storage had to be more than ingenious. It had to be dependable enough that a bank or factory could trust its records to it. The reason the final disks were 24 inches across begins with the physics of magnetic recording in the 1950s. Digital information could be represented by small regions of magnetic material oriented in different directions. A read and write head created those patterns and later detected changes in them. In principle, smaller regions meant more information on the same surface. In practice, the size of each reliable region was limited by almost every part of the system. The iron oxide coating was comparatively coarse. Disk surfaces could not be manufactured with the near-perfect smoothness expected today. The head could not position itself with microscopic accuracy. The electrical signal from a tiny region became harder to distinguish from noise. Motors, bearings, and metal structures changed slightly with heat and vibration. If the bits were packed too closely, the machine might confuse one magnetic transition with another or miss the track entirely. The IBM 350 stored information at an areal density of roughly 2,000 bits per square inch, unimaginably low compared with modern drives. To reach a useful business capacity, the engineers therefore needed a huge amount of physical surface. A 24-inch disk provided wide circular tracks and a large area on each usable side. Even so, one disk was nowhere near enough. The target was 5 million characters, equivalent to tens of thousands of punched cards. The size of the platters was not evidence that IBM's engineers lacked imagination about miniaturization. It reflected the limits of available magnetic materials, head sensitivity, mechanical accuracy, signal electronics, and manufacturing methods. A smaller disk would simply have stored less. A much larger disk would have produced greater weight, rotational force, bending, vibration, and balancing problems. 24 inches represented a practical compromise between recording area and mechanical control. The machine's enormous scale came from the fact that early magnetic data needed room. Each character occupied a physical territory that modern engineers would later shrink by orders of magnitude. In 1956, information still had a visible size. IBM used 50 disks because the required surface area had to be divided into a stack that the machinery could control. Each platter was made of aluminum, about 1/10 of an inch thick, and coated with an iron oxide magnetic material. The disks were mounted on a vertical spindle and rotated together at 1,200 revolutions per minute. 50 was not a magical number discovered in a formula. It was the outcome of engineering trade-offs. Too few disks would fail to reach the capacity target. Too many would make the cabinet taller and heavier, lengthen the access arm's travel, increase spindle stress, magnify vibration, and complicate manufacturing. The designers also faced a choice about reading heads. A later hard drive would often place one head near each recording surface, allowing an actuator to move all the heads together across the disk stack. The IBM 350 used a different and more economical approach. It had a moving access mechanism with two heads. One could face the underside of the platter above, while the other faced the upper side of the platter below. The mechanism moved vertically to choose a level and horizontally to reach the desired track. This reduced the number of costly precision heads, amplifiers, wires, and calibration circuits. The trade-off was time and mechanical complexity. The arm had to travel between disk levels before it could seek across a surface. Even so, average access was under 1 second, a remarkable achievement compared with searching card files or scanning tape. Picture the system receiving a request for a customer account. The arm rises through the stack, stops beside the correct pair of surfaces, moves toward the selected circular track, and waits for rotation to bring the record beneath the head. Within a fraction of the time required by older methods, the information becomes available to the computer. The 50-disk stack was therefore not only a container, it was a mechanical library whose shelves moved at high speed while a robotic reader traveled between them. Keeping those 50 platters stable was an engineering nightmare. At 1,200 revolutions per minute, on the outer edge of each 24-inch disk moved rapidly through the air. Any imbalance could produce vibration. A slight difference in weight, a small warp, an uneven coating, or a misaligned spindle could disturb the entire stack. Vibration threatened more than comfort. It could move the recorded track away from the head, weaken the signal, increase mechanical wear, or drive the head into the surface. Each platter needed to be round, flat, balanced, smooth, and consistent in thickness. The magnetic coating also had to be uniform. Too thin and the signal might become unreliable. Too thick or uneven, and the head clearance could change. Engineers experimented with ways to apply the iron oxide mixture and spread it across the aluminum through controlled spinning. They tested surfaces again and again because a defect invisible to the eye could become significant when the disk was rotating. Temperature created another challenge. Motors, amplifiers, and power equipment produced heat. Aluminum expanded as it warmed. Bearings changed behavior. Electrical components drifted. The head positioning system had to remain accurate while the machine moved from a cold start to steady operation. Dust was equally dangerous. To a person, a dust particle is nearly nothing. To a reed head floating less than 1,000th of an inch above a magnetic surface, it can resemble a boulder. Contamination could disturb airflow or damage the coating. The machine, therefore, demanded attention to air quality and maintenance that no punched card cabinet had ever required. When engineers opened an experimental assembly and listened to the disk stack accelerate, they were standing beside a mass of moving metal far larger than anything later associated with a personal computer. The sound, vibration, and airflow made the storage process physically dramatic. Yet the goal was to make all that motion disappear from the user's concern. A clerk should request a record and receive it without thinking about balancing, bearings, coatings, or spindle dynamics. The engineer's success would be measured by how ordinary the impossible machine eventually felt. The most delicate part of the IBM 350 was the read and write head. A magnetic head needed to approach the disk closely because the signal weakened rapidly with distance. But direct contact with a surface moving at high speed would create friction, heat, wear, and destruction. If the head scraped the iron oxide layer, data could vanish and debris could damage other tracks. The solution was to make the head fly. The IBM system used forced air to create a hydrostatic bearing, a controlled cushion that supported the head above the disk. The clearance was about 800 microinches, less than 1,000th of an inch. By modern hard drive standards, this distance was enormous, but by the mechanical standards of the day, it was astonishingly small. A separate compressor supplied clean, pressurized air. The head assembly was shaped so that air formed a stable film between the head and the rotating surface. The head had to remain close enough to detect the magnetic transitions, high enough to avoid contact, and steady while the access arm moved. The concept can be compared to a tiny aircraft flying just above a runway, while the runway itself races beneath it. Too high, and the radio signal disappears. Too low, and the aircraft crashes. Air pressure, surface flatness, head shape, and mechanical alignment all had to cooperate. This technology introduced the basic idea of the flying head that would become central to hard disk development. It also created the possibility of a head crash. If air pressure failed, if dust disturbed the cushion, or if vibration brought the surfaces together, the head could strike the disk. The first hard drive was therefore a machine balanced between proximity and destruction. Its data depended on a gap too small for a human eye to see. The separate air compressor added bulk and complexity, contributing to the unit's great weight and size, but without the controlled air bearing. The moving heads could not safely approach the disks closely enough to read the stored patterns. Once the mechanical system could rotate and position the heads, the engineers needed a logical method for organizing information. The disk surfaces were divided into circular tracks, and the tracks were divided into addressable regions. A stored record could be located by selecting the appropriate disk level, radial track, and rotational position. The drive held 5 million 6-bit characters, commonly translated into approximately 3.75 megabytes in modern terms. It is better, however, to remember the original measure because early character encoding does not map perfectly onto today's byte-based storage. The system organized the capacity into tens of thousands of records, enough to replace roughly 62,500 punched cards. These were not photographs, films, music files, or games. The IBM 350 was built for structured business information, product numbers, customer names, account balances, inventory quantities, payment histories, order records, and transaction details. Its power came not merely from storing the information, but from changing it. A punched card was a physical record. Updating it might require creating a replacement card and preserving the order of an entire file. A magnetic disk allowed a computer to rewrite a record at its location. An inventory count could decrease after a sale. An account balance could change after payment. A new order could be inserted into the working data of a company. The disk turned information from a static archive into something active. Random access did not mean literally instantaneous access. The arm still moved and the platter still rotated. But the computer could calculate where a record was located and command the mechanism to go there directly. The difference was like asking for a specific page in a book and opening to it rather than reading every page from the beginning. That simple shift created the foundation for databases, online transaction systems, and interactive business applications. The machine made stored information responsive. The disk drive was only one part of the IBM 305 RAMAC, the complete system announced in 1956. RAMAC stood for Random Access Method of Accounting and Control, a name that emphasized business use rather than technical glamour. The IBM 350 was the disk storage unit attached to that system. People often use RAMAC to describe the drive itself, but the distinction matters. The 305 included processing equipment, control units, card input and output, printing capability, a console, power systems, and the enormous 350 storage cabinet. The entire installation occupied a room and required trained operators and technicians. To understand what it offered, imagine a warehouse manager in the early 1950s asking, how many units of a particular product remained in stock? In a punched card process, employees might collect transaction cards, sort them by product number, run them through tabulating machines, and prepare a report. The answer could reflect yesterday's or last week's activity rather than the current moment. With RAMAC, the product number could identify a disk record. The computer requested the address, the access arm moved into position, the record was read, and the quantity could be displayed, printed, or updated. The system did not eliminate every delay or human step, but it introduced the possibility that a business computer could work with current records, rather than only process large historical batches. A bank could approach account information differently. A manufacturer could connect production decisions with inventory. An airline could imagine faster access to reservations. The IBM 350 did not create every later online service by itself, but it proved a necessary principle. A computer could maintain a large file and reach individual entries on demand. Processing and storage could operate as an integrated system, rather than separate worlds of fast calculation and slow retrieval. The road from laboratory prototype to commercial product was not smooth. Within IBM, some managers questioned whether the disk project was practical or profitable. The machine used unfamiliar technology, required precision manufacturing, and challenged established business methods built around cards and tape. A reliable commercial product had to survive transportation, installation, temperature changes, operator mistakes, and continuous operation. It also had to be serviced by technicians who had not designed it. The San Jose team needed to convert experimental rigs into documented assemblies with replaceable parts and predictable behavior. They had to establish manufacturing tolerances, testing procedures, maintenance schedules, and diagnostic methods. Louis Stevens became a key manager responsible for bringing the project toward production, while Johnson continued to guide the broader effort. The team's success depended on collaboration between mechanical engineers, electrical engineers, physicists, manufacturing specialists, programmers, and business planners. In June 1956, IBM shipped a pre-production RAMAC system with a Model 350 disk unit to the Zellerbach Paper Company in San Francisco. This delivery is generally recognized as the first commercial shipment of a hard disk drive. The storage unit stood roughly 5 feet high and 6 feet wide when its associated equipment was considered, and the drive with its separate compressor weighed more than a ton. IBM leased the Model 350 for approximately $750 per month as part of a larger system arrangement. That price represented a serious investment, but the value was measured against rooms of card files, labor-intensive searches, delayed reports, and the business cost of unavailable information. When the access arm moved and returned a selected record in seconds, the machine demonstrated something customers could understand immediately. Data no longer had to wait in line. The first commercial hard drive did not arrive as a small box sold in a shop. It arrived as infrastructure. Installing it required planning, floor space, electrical power, air compression, cables, trained personnel, and IBM support. Yet its very size helped reveal the scale of the achievement. The The cabinet held a physical landscape of information. The 50 disks formed 100 broad surfaces, and the access mechanism traveled among them like an elevator and railway combined. Each request became a sequence of coordinated actions. Interpret the address, select the level, move to the track, wait for the sector, amplify the magnetic signal, transfer the characters, and verify the operation. The user saw only the answer. This separation between complex physical action and simple logical request became a defining feature of computer storage. Later, programmers would ask an operating system to open a file without knowing the exact platter or track. Modern users touch an icon without knowing whether the data comes from flash cells, magnetic sectors, a network server, or a distant data center. The IBM 350 helped establish that abstraction. Information acquired an address that software could request. The machine's motors, heads, and disks became hidden servants of that address. What appeared to be a cabinet of machinery was also a new way of thinking. A company's records could become a searchable, updatable space rather than a procession of physical documents. The impact of the IBM 350 became clearer as later disk drives improved. Engineers increased recording density, refined magnetic coatings, strengthened error detection, created more precise actuators, designed better heads, and reduced platter diameter. One important development was assigning heads to individual surfaces, allowing an actuator to move them together rather than carrying one pair vertically through the stack. This shortened access time and reduced some mechanical complexity. Removable disk packs appeared, allowing operators to lift a collection of platters from one drive and replace it with another. 14-inch disks replaced 24-inch disks. Later came 8-inch, 5.25-inch, and 3.5-inch formats. Each reduction depended on storing more bits in less area. By the late 1970s and 1980s, hard drives were becoming small enough for mini computers and personal computers. A desktop owner could store programs and documents without loading everything from floppy disks. The drive, inside the case, still carried the fundamental descendants of RAMAC: rigid magnetic platters, a spindle motor, movable heads, circular tracks, and direct access to chosen regions. The machinery became sealed, quieter, cheaper, and more precise. A device that once weighed more than a ton eventually fit in a pocket. Capacity grew from millions of characters to millions of megabytes. The distance between the head and disk shrank from hundreds of microinches to dimensions measured in nanometers. Aerial density climbed from thousands of bits per square inch to trillions. These improvements were not one sudden invention, but a chain of advances in materials, electronics, control theory, manufacturing, and software. The first disk drive did not predict every step, yet it defined the challenge that generations would continue to solve: place more information on less surface and reach it faster with greater reliability. Solid-state drives eventually removed the spinning disk from many computers. Flash memory stores charge in electronic cells and has no access arm, platter, spindle, or flying head. It can operate silently, resist mechanical shock, and reach data with very low latency. At first glance, the SSD may seem to end the story begun by RAMAC. In reality, it confirms the expectation RAMAC created. Users assume that stored information can be reached directly. They expect a system to open one file without reading all earlier files. They expect records to change immediately and remain available after power is removed. Whether the physical medium is a magnetic disk, flash memory, optical storage, or remote cloud infrastructure, the logical relationship remains familiar. Data has an address, and the computer can request it. The IBM 350 was the first commercial machine to make that expectation practical at a meaningful business scale. It transformed the value of storage. Before random access disks, storage was often an archive through which information traveled in sequence. After RAMAC, storage could become part of an active conversation with the processor. This shift made interactive databases possible and encouraged businesses to place more of their daily operations inside computers. The future of banking, reservations, inventory control, and online commerce depended not only on faster processors, but on storage systems that could retrieve individual records quickly. A processor without accessible data is like a brilliant clerk locked outside the filing room. RAMAC opened the door. So why did IBM use 50 giant disks to build the first commercial hard drive? The answer is simple in principle and extraordinary in its consequences. In 1956, reliable magnetic bits required far more physical space than they do today. The iron oxide coating, head design, signal electronics, motor control, positioning accuracy, and manufacturing techniques limited how closely information could be packed. IBM needed enough surface to store 5 million characters, a capacity large enough to replace tens of thousands of punched cards and make the machine useful to businesses. 24-inch platters provided wide tracks, and stacking 50 of them created the necessary area within one cabinet. The moving two-head mechanism reduced the number of expensive precision heads. The forced air bearing allowed those heads to approach the surfaces without touching. The huge spindle, compressor, and access arm were not signs that the engineers had failed to make storage small. They were the tools required to make random access storage possible at all. Every part of the machine was a compromise between capacity, cost, precision, speed, and reliability. The 50-disk stack was where the available technology met the desired business result. Its capacity may look tiny now, but the important number was not 5 million. The important word was random. For the first time, a commercial computer could reach one stored record without processing the entire sequence before it. Reynold Johnson and the San Jose team gave computers a new kind of memory. Not memory in the temporary electronic sense of holding an active calculation, but memory as an organized world of records waiting to be revisited. Their machine had no polished screen, no miniature connector, and no silent elegance. It announced itself with moving arms, spinning aluminum, compressed air, and the weight of industrial equipment. Yet inside that motion was the ancestor of an experience now so common that it is almost invisible. When a person searches for a customer, opens a document, checks an account, or requests an old photograph, the system goes to the desired information rather than forcing the person to examine everything stored before it. Today, billions of files can fit inside a silent device smaller than a hand. Data centers hold information on a scale the RAMAC engineers could scarcely have imagined. But the journey began with 50 magnetically coated disks turning inside a cabinet that weighed more than a ton. The machine stored less information than many modern photographs. Yet it changed the direction of computing because it proved that data could be found, changed, and used in seconds. The next time a file opens almost instantly, remember the engineers who once balanced 50 giant platters, floated ahead on a cushion of air, and listened to a mechanical library spin. They were not merely building a large storage machine, they were teaching the computer where to find its own past.